Good afternoon, everybody, and welcome back to the 10th lecture of Visum and applying transport modeling with Visum. I'm again Guido Cantelmo. We did together the first classes of this semester, and today we are going to go to the class called Traffic Assignment. So, first of all, today we are going to look at what traffic assignment is from a methodological point of view. So first of all, we are going to introduce the concept of shortest path, route enumeration, route choice, and traffic assignment. After reviewing overall the entire concepts, we will go into more details in how can we model traffic assignment in Visum specifically. So a brief review of traffic assignment, something that in principle many of you should already know from other courses within the Master of Transportation Engineering, but that in general we want to be sure you know before you put your hands in Visum. So we already discussed this framework. This is the typical framework of a transport model. A transport model is a model that represents choices. And this model is composed of three different levels. We have the supply, which is represented the transportation facilities and service, together with the characteristics of these services, such as the capacity of a certain road segment. The supply is influencing the level of service, which means how good our infrastructure is and how bad it performs when it's heavily congested. Then we have the demand, which is how many people are actually using this infrastructure and how they decide to move on this infrastructure. Do they decide to go with a car? Do they decide to go with public transport? Of course, the interaction between supply and demand depend from what we call an activity system. The activity system is the reason why people move. People move to go to work, people move to go to school, people move because they want to achieve certain purposes, like even just leisure activities, such as taking a beer. So it is extremely important to properly model the correlation between these three systems. And this is where we use Visum. Visum is a software that allows us to properly analyze the correlation that exists between these three different entities. And specifically, the interaction between what we call the supply system and the demand system is usually called traffic assignment. So when we talk about traffic assignment, usually we are talking about the combination of supply and demand. So what do we need to combine the supply and the demand? Well, first of all, we need to know the demand, how many people are moving. We have already been seeing this during the course. So what do we need to know? We need to know the trip origin and the destination, where people are going, where they are coming from. For dynamic models, we also need the departure time. Are we talking about the morning, the evening, 8 o'clock, 5 o'clock? What do we get? Well, the traffic assignment takes as input the demand with all the characteristics that we've been discussing and gives us, So as I was saying before, what do we need? We need the demand, how many people are moving. We need their origin, their destination, where are they coming from and where they are going. And we need for dynamic models departure time. Once that we have this information, together with the supply characteristics, the traffic assignment model gives us traffic volumes on each road segment. And of course, they give us also other data. They give us speed, densities. If we're talking about public transport, we can also get other information, such as how many people are using this specific line. So what do we need? Well, if we're talking about private transport, what we need in order to actually obtain this output is, first of all, a route set generation. So route set generation, it means that for a given origin and for a given destination, you might have a lot of different routes. In this example, we are looking at three different routes. Some of them partially overlap. All of them actually partially overlap, at least at the beginning. And then they have different parts that are not overlapping. Of course, we could consider many more routes. We could consider some routes that are passing, for instance, for this area of the network, or for this yellow part over here. So the route set generation tells us how many routes we want to consider in our problem. Is 3 enough? Should we consider 5? Should we consider less? The second information that we need is the route cost. Once that we have several different routes, which one is the cheapest? And we will see the concept of route cost in a minute. Finally, we need some decision rules. Obviously, certain routes will be neglected, either because they are too expensive or simply because they do not make sense. So let's start from the first problem that we need. We talked about route sets. When we talk about route set, we are talking about limiting, first of all, the number of routes essential in a large network. What does it mean? It means that if we consider a network like Munich, and if we consider as origin Garching and as destination the campus in downtown, there are almost infinite routes connecting these 2 points. If you consider that 2 routes that are very similar but have just one small difference in one of the small segments, that's already enough to define 2 different routes. So if you consider all the links in the network and all their combination, we have a very large number of routes, a very large number of options, which are usually not necessary. Users do not process too many alternatives. If you think about yourself, if you think about going from Garching to the campus in downtown, you will probably not consider all the possible routes, you will not consider all the links in the network, but you will consider a few options. So which one we need to keep? How many of these options that you are considering are actually overlapping? Should we consider routes that overlap the same or not? And if so, how do we distinct them? What do we mean for overlapping? 100% overlapping? 70% overlapping? Another thing that we need to consider is that some routes, of course, need to be removed a priori because they are not very reasonable. For instance, all routes that involve loops are usually not considered. A loop is when you cross the same intersection twice. So usually you don't want to cross the same intersection twice when you are traveling from one point to the other. So all these routes that generate loops are usually removed from the network. We also want to remove those that make extreme long tours. For instance, assume to exclude those with more than 3 times the distance of the shortest route. So we do know what is the shortest route. The shortest route is the fastest possible route, but the fastest possible route when we don't consider congestion. If there is some congestion, you might choose a different route, but probably you will not choose one that is 3 times more expensive. So this is another criteria that is usually used to neglect routes. And finally, those involving large part of trips on opposite direction of the destination. So for instance, if you have to travel for a very long time in the opposite direction of your destination, that's usually not very convenient. Of course, a large part of the trip, we have to consider what we are talking about. Finally, a common approach for route set generation is what we call empirical selection. Use routes may be identified using data, for instance. If you have GPS trajectories, you might just try to use GPS trajectory to observe which routes are used from traveling from one part to the other of the network. Of course, there are some limitations here. For instance, that new routes cannot be observed directly from the data. So when we want to plan new facility or just manage our network, this could not be the best solution in general. So we have to be very careful with that. As I mentioned before, one of the options is usually to take as reference the shortest path. So what is the shortest path? There are many algorithms to calculate it. The most famous one is by far the Dijkstra algorithm. The Dijkstra algorithm finds the shortest path between an origin node S and a destination node T in a network. So the algorithm searches sequentially for each origin node or centroid the shortest route to all other nodes in the network. Here we can see an example. If we want, for instance, to know the shortest path from node 1 to all the other nodes in the network, actually to all the other nodes in the network that are represented in yellow, then this is the shortest path 3 of node 1. So talking a little bit more, being a little bit more specific, what is the difference between a network that is a tree and a general network? A general network is the one that you can see in the left. And this is characterized by many different possible routes. For instance, one of the typical characteristics of a general network is the presence of loops. For instance, if you want to travel from node 1 to 2, you can actually travel from 1 to 2, or you can travel from 1 to 3 to 2. And eventually, a loop is the possibility that from 2, you can travel to 5, then to 3, and then back to 2. In a tree, the difference is that we never have loops. So we only have one possible route connecting different nodes, in this specific case, node 1, 3, 2, 5, and so on. And thanks to Dijkstra, we can build what we call the shortest path tree, which means that the paths that you can see here that connect the node 1 to all the other nodes in the network are the fastest or the shortest path. What is the shortest path? It means that, for instance, if you want to travel from 1 to 5 and you use this route, your total cost will be 10 plus 3 plus 3 equals 16. There are many other routes. For instance, you could just travel from 1 to 2 and from 2 to 5, but these will have a cost of 16 plus 3, 19. And this is not something you want. You want to start from the best option. Once that you have created the best option, the fastest option, then you can use this one as a starting point to create other routes. As we said before, for instance, in this case, we saw that the shortest path is equal to 16. So everything that is longer, for instance, of 2 times the shortest path, so 32, we might not want to consider it because the network is relatively small. And by using this rule, we can create a series of paths which can be used to model the connection between different nodes in the network. There are other options. One is what we call explicit route enumeration, which is enumerate all possible alternatives. This is, of course, feasible for small network, usually not so common for large networks such as the network of Munich. Labeling approach say that route sets include the most convenient route taking into account different characteristics, labels. So for instance, we might say that we can calculate the shortest time in distance, the fastest route, so the shortest time, the shortest route, the shortest path in terms of travel time. We can calculate the most reliable route, and we can see, okay, we have different routes. Each of them is the optimal solution according to a specific characteristic that we set, and we use this one to generate our initial set of paths. And finally, quite common is the so-called constrained k-shortest path. Find a set of paths by successively selecting the first, second, and k-shortest path, which basically means you keep running the shortest path algorithm until you find a series of trees which is basically suboptimal. The basic formulation uses, however, unrealistic or similar routes. The algorithm basically works by changing a little bit the network and changing a little bit the cost at each iteration to generate different routes. But again, the normal shortest k-shortest can create similar paths. So very often we use constraints to avoid this issue and improve the efficiency of the problem. So the route set generation is what we call the first part of the traffic assignment problem. We have the demand and we have a set of routes connecting each origin to each destination. Now, however, we need to assign the demand to the route, which means that for each, let's look at the example here, for instance. We have one origin destination, or the origin and destinations are in blue, and we have two paths, route A with a travel time of 2 minutes and route B with a travel time of 6 minutes. Now, intuitively, anybody will choose option A because it's the fastest. However, this is not necessarily true all the time, and even more important, the fact that route A is the most convenient depends on how many people are using this route. For instance, if everybody uses route A and we have congestion on route A, then the travel time could become from 2 to 20 minutes, and suddenly route B is more convenient. So we need to pay attention to all a series of models that tell us how people choose. The most common model in its most basic formulation is what we call the logic model. The logic model represents the set of choices as a tree. So in this specific case, for instance, we have alternative A and alternative B, each of them associated with a certain cost, 2 and 6 in this case. Then we can calculate the probability of choosing each of the two options as a probability, which is given by this equation on the top. The equation on the top is basically saying that the cheapest option, in this case A, is more convenient than the other option. However, there is one parameter what we call the scale parameter of random residual theta, which tells us the stochasticity of the problem. Once that we decided that alternative A is more convenient, we need to understand how many people are going to take the most convenient options and how many people will basically take the option that is suboptimal. Now, if theta is equal to 0, basically this model becomes deterministic, which means everybody is going to take the alternative that is the most convenient. It doesn't matter if the difference between route A and route B is 1 minute, 1 second of 300 hours. The result is that as long as alternative A is more convenient, as long as it's more convenient, people will just take alternative A. By increasing, basically, by increasing the value of theta, we can increase the stochasticity of the problem. So this is also shown in this picture over here. For theta equal to 0, you can see the deterministic choice. On the x-axis, we see the difference between the utility, VB minus VA. So if the cost, actually not the utility, the cost of B is higher than A, we are in this side of the graph, and we see that the probability of choosing A is 0. On the other opposite, we can see that the probability of choosing A when the utility of A is actually bigger, it's actually equal to 1. So the reason why you're seeing here is because the model maximizes the probability to choose a certain utility. The utility can be, for instance, the negative of the cost. The utility is always positive, and we always try to maximize the utility. The point is that this graph that you can see here in red, this step, represents the deterministic decision. In the moment in which one of the two alternatives becomes more convenient, you go for that one. So in this side of the graph, you can see what happened when the utility of traveling by A, which means when the cost of A is actually smaller than the cost of B, we choose option A. And in this side, we can see what happened when the cost of the alternative alternative B is actually more convenient, which basically means in this specific case, people are going to use alternative B. If we increase the value of theta from 0 to 0.5, 1, and 2, we can see that this probability slowly start changing its shape. And now we'll have that even if the alternative A is more convenient, still some people will decide to go with alternative B. And if we push theta to the extreme, actually, we will have a uniform distribution, which basically means that a user will choose either alternative, will just simply choose 50% of them alternative A, 50% of them alternative B, no matter of the cost. So the parameter theta is very important to have a realistic distribution of the flows over the path. And specifically, we usually want to have something which is neither zero, so we don't want to have the deterministic, but for sure we want to have something that can take into account the difference into the cost. The parameter theta is very important in this sense because if you don't calibrate very well this model, then you will never get actually a good distribution of the value, a good distribution of the demand over your two routes, and as a consequence, you will never actually get a good assignment model. Finally, the standard logit model is a little bit too simple to model complex behavior. We already say that basically what happened here with the logit model is that we simply model a probability based on the travel time, or based in general of the utility associated to a certain route. Now, what happened here is that if, for instance, we have three different routes, A, B, and C, and we model them with the normal logit, what happened is that we will have three different alternatives. And specifically, alternative B and C will be perceived as completely different alternatives. This means that, for instance, if we assume that the probability of choosing each of these route is the same, so we assume a uniform distribution no matter of the time, we will have the 30% of the people will choose, So this is another example, as I was mentioning before, the slide wasn't updated, in which we have one origin and one destination, but we have three different routes connecting them, A, B, and C. B and C are pretty much the same route. They just split at the very end, and they have the same travel time, at least in free flow condition. So if we decide at a certain theta for which the probability to choose each of these routes is the same, a normal logit model will tell you that you have 30%, 33% roughly probability to choose alternative A, and the same probability for B and for C. However, this is clearly not correct because alternative B and C are actually correlated. All the people, in this case, we will have the 33% of the people will take alternative A, but 66% of the people will actually share this part of the route, which is quite large amount of it. So what we need to do is to explicitly consider this correlation. We are not going to go through the model, but the point is that there are models. One of them is the so-called C-logit, proposed by Cascetta in 1996, that adjust the logit in order to take into account the correlation between routes. So why this is important? Because this is one of the models that you can use in Visum. In Visum, you can use the logit models, you can choose the parameters theta, and you can decide to use the C-logit or other models to consider correlation between different paths. And it's important to understand that all these parameters are parameters that you need to calibrate at a certain point. If you decide a wrong value of your C-logit or a wrong value for your logit model in general, you will probably never be able to have good results in Visum, no matter how well you design the network, no matter how well you design the demand. So now we have all the elements that are needed for getting the for actually making our traffic assignment. We have the demand, we have a set of routes, we have the cost of each route, and we have a choice model, which tells us how people choose the different routes. So the problem of the traffic assignment is, given an OD matrix, find route flows that are consistent with route cost. Traffic assignment models simulate the interaction of demand and supply on a transport network, as we mentioned before. And we can distinguish basically between two of them. What we call static assignment, which is the one we are dealing in this course, is usually divided in what we call uncongested assignment and congested assignment. So if you look at the definition of a problem, what we see is that route flows, we are looking for route flows that are consistent with route cost. What does it mean? It means that you will make a choice eventually, but you will choose the best possible route. So if usually when there is no congestion you are choosing a certain route, when there is congestion, you will probably choose a different one. This is called the equilibrium problem. You will look for the shortest path at a specific time of the day, which is the moment in which you want to travel. So in uncongested assignment, the shortest path is constant. So costs are independent of the traffic flows. In simple words, the road network at night is empty, so it doesn't really matter if you are traveling or not. It will not influence the traffic, the cost for other users, because there are not so many users, so there are basically very limited interaction between users. Congested assignment, on the other hand, is that the cost of the route depend on the flows. This is the case, for instance, of the morning commute. The fact that you want to use the city center, or you want to use, for instance, the ring, the motorway, will depend on how many people are using it. For instance, once again, traveling from Garching to the downtown campus in the morning takes way more time than in the evening, or actually than at night. Why? Because you have way more people going towards the city. So when you have congestion, you have that the number of people using the infrastructure will influence the travel time. And this is what we call congested assignment. So the route choice do not suggest better option. Route costs do not change anymore. This is what we call equilibrium. You can take equilibrium as a sort of day-to-day learning process. You start today, you choose one path, and you learn that it's very congested. Then tomorrow you may choose a different path. Then one day you will realize that one certain path is actually the most convenient during that time of the day. But this choice that you're doing depends on other people's choices. And this is exactly what we call congested assignment. In uncongested assignment, your decision is mostly an individual decision. The choices of other users do not really influence your decision in the end. And this is more or less what Wardop's first principle of user equilibrium says. This is the basic logic behind most traffic assignment models. The user equilibrium principle says that the journey times on all routes actually used are equal and are not greater than those which would be experienced by a single vehicle on any unused route, which translate in the travel time or the cost of the route used by travelers between any given origin and destination are the same and or shorter than any of the unused routes. Basically, at the end of the day, if you choose two different paths, these paths need to have the same travel time. It doesn't matter the initial travel time when there is no congestion. When there is congestion, all used paths traveling from one origin to one destination needs to have the same travel time. Why? Because if you find out that there is a better path, you will move to another path. So at equilibrium, you are sure that the path you are using is the best possible one. So, reviewing very quickly the whole procedure, the traffic assignment main steps is divided in three parts. First of all, we need to generate a route set. So, which sets are considered by users when traveling from one origin to another one, to one destination. Are we talking about the most reliable path? Which algorithm do we use to select these paths? The second option is the route choice. Once that I have a set of options, how do I choose? Is it deterministic or a stochastic choices? This is very important to take into account user perception. We did this example during the first class. It depends also on the mode you are considering. For instance, if you are considering public transport and you are considering the users have real-time information, then the model should be closer to a deterministic one. Why? Because if people have access to the information and know that at this specific instant a certain option is more convenient, they will very likely go for that one. When we are talking about usually users driving their own car, the process is a little bit more stochastic because you never have real information about what happened. So stochastic, it means that routes that are very similar will have similar flows, similar type of demand. Of course, we have also to consider when we do route choice spatial correlation, because once again, we don't want user to choose different, we want to take into account the fact that certain paths are have long common parts, and this should be considered in the choice of people. You might decide to discard one option just because you know that there is a bottleneck at a certain intersection, even though people are going elsewhere. Last but not least, you should always remember, as I was mentioning before, the transport cost is not only travel time. So as I was showing before, travel time is one option, but for instance, you might also have tolls. If you have a motorway with tolls, then you suddenly might have an option that is better in terms of travel times, but you have every day to pay, for instance, €5. This will make it way less competitive than an option that maybe takes a little bit longer but is free. Last but not least, you have the equilibrium concept. No user will choose a suboptimal route. All users will take the best one. So if we are talking about an uncongested scenario in which basically each driver doesn't really care about what the other users are doing, which means constant travel time on all routes, then each user will choose the shortest path. If we're talking about congested scenario, where the route costs depend on the route flows, which means the decisions of other people influence your own decision, then you have an iterative process in which users try different routes, different options, until at a certain point they find the so-called point of equilibrium, in which the travel cost of all the routes is actually the same. One last comment, something that it's good to know, as actually Visum does offer also the opportunity to do dynamic traffic assignment, is the difference between what we call dynamic and static models. A static model is a model where the demand is constant over time. These usually represent average values, and traffic volumes can exceed capacity. The reason is that you don't have queue or spillback, and in general, these models are more reliable but less realistic. What does this mean? It means that, for instance, in models like this one, you will assign at the same time all the vehicles that you assume are moving during the rush hour, for instance. And you will get an average volume on the network, and if there is congestion, you will know that by looking at the fact that there is more demand than supply. So when you know that there is on a certain infrastructure more demand than supply, you know that there is congestion. However, this is something that is physically impossible. You cannot have more vehicles than the actual capacity of the infrastructure. And this is why static model actually represent the average values. It means that on average, in that hour, you have more people traveling than actually how many the infrastructure can accommodate. In reality, what happens is that because the demand is higher than the capacity, you will have what we call spillback. We will have congestion, and we will have queues, which are not usually modeled in static models. And this is why we allow in static models the model to exceed the capacity. It is more reliable because it's usually a simplified model, so it's more robust, but it doesn't provide really good insights in terms of congestion. If you want to understand when the congestion is, these models will not be able to really give you this information. If you are interested in congestion, you should use instead dynamic models, where the demand varies in time. In a dynamic model, the volume of traffic is described at each time interval, and flows propagate over time. This means that if suddenly you have an excess of demand, which is larger than the capacity, you will not anymore observe a larger demand on a certain link. You will just observe spillback. You will observe congestion propagating on the network. And eventually, the excess of capacity, the excess of demand for one link can create bottlenecks and congestion elsewhere in the network. So when should we use dynamic models? Well, dynamic models are usually less reliable, so we don't really use them so much for planning, but they are way more realistic. So for instance, if we want to represent congestion, if we want to do real-time traffic predictions, then we should definitely go for dynamic models. So this was a relatively short introduction to what traffic assignment in Visum, or what traffic assignment is. Now we're going to look a little bit how we can play with these elements in Visum more specifically. So, in these slides, we are going to see how to do the traffic assignment for the evening trips. So, for instance, only trips starting from home have been used for trip generation and distribution and mode choice. The trips that start from home are expected to return by the end of the day. So what we can do is that we can imagine the return trips as a mirror reflection of the trip starting from home. What does it mean? It means that if we have created a certain matrix for the home-related trips in the morning, we can just do the transpose of this matrix to observe the trips during the evening. Suddenly, we switch, by doing the transpose, we are switching origin and destination. So if before we have 20 people going from origin A to destination B, now by doing the transpose, we have 20 people going from origin B to destination A. Why we want to do that? Because it's actually very convenient in Visum. We will see that also with a practical example with the software. But in this slide, you can find all the information for that. Once again, the reason is that Visum provides several tools for doing different operations with matrices so that you don't have necessarily to do over and over the same operation again. So for instance, if you want to create a matrix, we have already seen how to create, for instance, matrices for different modes or for different activities. In this example, for instance, we had the matrix for all the home-based trips done by car. And if we want to create a new matrix, what we can do is to click on Create Matrix, select again Demand Matrix as before, but now instead of Data Matrix, there is some delay in the slides updating. So I will repeat from here. As I said before, there are several ways of creating matrices in Visum. One of them is to create manually the matrix. So you can create a matrix from here. Once that you are in Matrix Editor, we will do that in practice anyway. And then you can select Demand Matrix and you can select Data Matrix, and you will have to manually fill this matrix. Another option is that you can use Formula Matrix to create artificially a matrix starting from some other information that you already have. So in this case, for instance, we can take the matrix for the morning commute and just make the transpose, which is this operation over here. And this will create automatically a new matrix. Now, you will be able to view the new matrix, and this will be not anymore under data matrix, but will be under Formula matrices now. You can repeat the same procedure to create, for instance, evening trips for all the remaining transport modes. So you can do it, for instance, for also bike, public transport, and so on. This is quite convenient and is avoid you to, for instance, use Excel or any other software to manually do this operation and then repeat over and over. Additionally, if you do any operation on the morning commute, in this way you will automatically work on all the other matrices. So it's definitely more convenient to do when you have to create a relationship between matrices. It's always more convenient to actually use this option in Visum directly. Okay, before going to the next step, let's try to do this one. So I'm opening Visum. And this is still the training version with 45 minutes. And there you go. We have our network, we have several different matrices over here, and we want to create a new matrix. So if we want to create a new matrix, what we have to do is to go, as I was saying before, in create new matrix. It doesn't matter which one I'm creating. So at this point, I can create a new matrix with the name I want. Let's say for instance, this is the evening commute by car. We give the same name to the matrix too. The type of matrix we already said has to be a demand matrix. And here, instead of data matrix, which is what we've done before, we can use formula matrix. And then we can click Edit Formula to introduce a new formula. Now, the first thing that we want to do now is to introduce a function, we say. We want to do the transpose of the matrix of the morning. So we can click on this symbol, which is insert a function. We can look for the transpose. There you go. And select OK. So now we have a function, but as you can see, we have an error here. The number of argument 0 of the function transpose is invalid because we have to select a variable. So the variable is the matrix we want to make the transpose. And this is, in this case, matrix 12. Mode choice, home-based, work-related trips by car. So at this point, I have no error. I have my function, I have my variable. I can click OK. OK again. And as you can see, I generated a new demand matrix, which is not anymore in this part, but is in this part over here. And if, for instance, I click on this matrix over here, so the original matrix, and I suddenly say that this is not 8, but is, actually, let's go on the diagonal. This number is now, for instance, 100. You can see that now I change the demand value also in the transpose. So every time that now I do a change in the original matrix, I don't need anymore to take care of what happened in the other matrices because the formula will take care of that for me. And of course, you can do similar operation for other matrices, such as the evening commute, such as public transport, for instance. So same thing, demand matrix, formula matrix, edit formula. We have to insert first the function in this case, transpose, variable. This time it is going to be public transport. And we created a new one. So this is how we basically create metrics in so this is how we can create matrices with the formula from the one we already created before. Now, the next step is to allocate matrices to demand segments. So what does this mean? This is actually a very important element to take into account when you're working with Visum. A demand segment is what eventually gets assigned to the transport network. So the demand strata of the modes are generally aggregated to create demand segments. For example, if you create different matrices for trips by car, you might want to assign all of them to the assignment of private transport, because at the end of the day, they will compete for the same infrastructure, so you want to assign them together. And this is what a demand segment is. You decide what is assigned to what. To decide the demand segment, first of all, you need to go from the demand menu to demand data. And in demand data, you can select first demand segments. For each demand segments, you can assign at this point one of the different matrices that you want to use. So you can directly click on demand segments, matrix, select a matrix, and you will be able to assign this or whatever other matrix you want to assign. And that's it, basically. This is how we assign the matrices to demand segments. So let's look once again how we can do that. So we say now that we have our demands, we have to go in demand data. We have the demand segment code, so we have bike, car, public transport, and so on. If we want to select the demands, we can just select matrix. You can, in this case, there is select matrix by properties. This is also another option. It's similar to using formula basically, but in this case we want to select matrix directly. So we want, for instance, for car to select the mode choice car. And now we have that the matrix that is assigned is matrix 12. Similarly here, we can go again, select matrix directly. We are in public transport, so we can assign the public transport matrix. And for bikes, we can assign bike. And with this one, we should be able now to have basically assign each matrix to one specific demand segment, as we can check again by checking the demand data. As you can see, this is the matrix that we selected before. So the last part is actually create private transport assignment procedure. So this is the last step. We have done everything we were supposed to do. Fortunately, we don't have to generate a route set because Visum will by default create a route set for us. So we can directly select the calculate menu and select procedure sequence. In procedure sequence, we can then click on create icon, which is over here, and select private transport assignment and click on OK to create the private transport assignment procedure. We can then select reference objects. We can then select here as reference object the type of demand segment that we want. So for instance, we are talking about car, bikes, or whatever. And here we can select, for instance, the demand segment we want to select for this specific procedure. Of course, when it comes to private transport, we can only select bikes or car data. Finally, we can decide different options or variant files. So we can usually go for different procedure for the equilibrium. So we discussed it already, is equilibrium assignment. The other one we also discussed conceptually is the stochastic assignment. We have dynamic user equilibrium, we have dynamic stochastic user equilibrium. In this example, we actually go to use stochastic assignment because it's the one we have looked before. And once that we go in the stochastic assignment, we can actually open the several parameters for the model that we are using. And we can, for instance, select the type of model we want to use. We can, for instance, say, okay, we want to use a logit model, and we can decide the beta. As you can see, here is a negative beta. That's because we want low travel times to be more convenient. And we have the scaling R, which tells us how stochastic our model is. We can also define the impedance based on the travel time or on the length. And we can do it, we can include the coefficients calculated according to Cachette or to Ben Akiva to consider the correlation between paths. So everything we have seen in the first part, you can play here with the parameters to see what happens when we change the stochasticity, when you consider the correlation between paths or when you don't. So before moving to the public transport, maybe we can give a look to these elements also in Visum. So to open the procedure sequence, we say we have to go in calculate first and procedure sequence. So this is too small. There you go. So now it should fit entirely in the window. So now we can click on create a new model, and we want to create, as we say, private transport assignment. Can click OK, and we will have created over here a new procedure which is called private transport assignment, as you can see here. We can then select the demand segment. In this case, we want to assign cars, and the variant file. So, as I said before, now I want to use the stochastic assignment model. So now I put together everything I wanted. I have, I have the procedure. I want to do the assignment. I know which object I want to assign, car, and I know which model I want to use to represent the correlation between the choice of the user to use one route or the other, which is stochastic assignment. But as said before, I can go even better and look at more options to personalize and to make this procedure better. How can I do that? For instance, play with the edit function. If you click, so if you select a specific procedure and you click on edit, you will open a list of options that you can use to personalize the model and to change it. So as I said, the one I'm interested to show before is the choice model, because it's the one we introduced before and is extremely important to have an accurate representation of how people actually move in the network. We have different models of choice. In this case, we want to use the logit. Once that we select the model, we have here the description of the model. So the equation is changed, for instance, with respect to the one we had before. We have the coefficient, the value of the coefficient beta, which by default is 0.25, but we can change it. And we have the scaling factor I was mentioning before, which is R. And finally, we can decide once again if we want to calculate the impedance based on travel time, based on the length, if we want to use the equation from Cachetta or from Ben Akiva to calculate the correlation between different routes. And if you see, if I run the assignment, which is just clicking here, the message says that the assignment worked perfectly. So the model that we created runs and doesn't provide any problem. Okay, so for the last part of this presentation, we're going to now to see how the traffic assignment works in Visum. So traffic assignment is different, as we've seen, for private transport and for public transport. There are several ways, and you may already know that, including the fact that we assign different type of demands. So we need to create a different procedure when we want to assign also public transport. And in this case, we will have to follow pretty much the same procedure as we did before. So we have to click on create. We have to select public transport assignment. We will have to select between different options. In this case, we want to use the timetable based. And of course, this only after that you have selected as referent object public transport. If we double click or if we click on the dialog box for defining editing, we can also here play with the different settings of the simulator that we want to use. And that's pretty much it for the public transport assignment. So again, we can just quickly go through it in Visum again. So still from the procedure sequence, so in case you are lost, calculate procedure sequence, you can create a new procedure, public transport assignment, click OK, reference the object, public transport, timetable based, and now, for instance, they are both selected. We can again either double click or just click on edit to see the characteristics of our model, and including the search algorithm. For instance, here we are using a branch and bound. Again, we have the choice model once again. For instance, we can set the logit model, the same as before. There are several different models, the several different parameters. All of these are described in the help, and you should definitely look for them when you need something very specific. But in general, let's say the most widely adopted, as we say, is the logit model, and it works fairly well in general. And as you see, I clicked run, and now I managed to assign both public transport and private transport at the same time. The assignment process is sequential, and the reason is once again that the assignment is quite independent. Specifically, the choice is different between people choosing public transport or choosing private transport. But the point is that right now on the network, we will have, let's see if I can show. There you go. If you look at the network, okay, this is a little bit messy. Let's remove the connector. If you can see on the network, now you can see all these different colors. These different colors represent different people doing different choices. And specifically, you can see that there are more people taking these routes, and there are a lot of people also taking these routes, which is clearly public transport. Why? Because the main public transport line is here. And this is exactly what we also show here. If the procedure has been performed successfully, you will be able to actually see the output of the results, which is the number of the assignment for the public transport and for the private transport. How do you know that this is public transport or private transport? And even more important, how do you know what you're looking for and why you're looking at that for? Well, you can use the graphical parameters. So this applies pretty much to all the information that you want. You can do the same for links, but for nodes. But if you want, for instance, to look at what happened on the links, you can simply click on links, right click on links, go on graphic parameters, go on bars, and you will open something like a menu like this, where you will have different options. So for instance, now you can see that at the moment in red, you have the volume with private transport, and in blue, you have the volume with public transport. If you want to show something different, if you want to change the color, if you want to change the scale, you can do everything from here. How to edit the assignment output. To access the list, you can access the list of links from the list menu on the network. So it's once again you can go on list, network, links. You can also right click on links and go directly for list. But alternative is list, network, links, and you will open this information, this table over here, which means that we have seen, I think, this already before, but differently from what we were seeing before. Now you don't only have the characteristics of the links in terms of link ID, number of links, characteristics of the links, length of the links, number of lanes, capacity, but you also have the actual number of people traveling on this link, whether that is private transport or public transport. This is some homework from private transport, or some exercise, more than homework, for private transport and public transport. You should try to do the assignment for the return evening trips. So basically this means that first you have to create the matrix for the evening trips, like we have seen before until now, allocate the matrices to the demand segment, perform the stochastic traffic assignment, and analyze the simulation output for different choice models. This will be, so basically playing with the scale parameter will help you a lot in understanding how this parameter can change entirely the output of your model. And it's not something that you should take lightly, because once again, you can have the best possible model. You can have spent a lot of time in calibrating your network, in having an accurate representation of the supply, an extremely realistic representation of the demand, and still, if you're not careful about this parameter, your model will provide very unrealistic results. Task 2, for those who are really willing to see what happens by changing the parameters of the model and how the outputs of the model can change drastically by changing a few parameters, you can try to change the volume delay function. You can see how to change the volume delay function in the lecture, on the second lecture on the supply. And specifically, you can see what happens if, for instance, you try to change the parameter A and B of the BPR function. Finally, always remember that the manual will help you, and that Visum has the tutorial in English or German that is located under the quick start. All this information can give you a lot of additional feedback on these tools if something is unclear. Plus, of course, you can always write to me if there is anything. As usual, my contacts. And now, before leaving you to your exercise and homeworks, I would like actually to show you how to play with the graphical parameters that I just introduced. So once again, we have our network over here. As I was saying before, in red here we have the volume with the private transport, and in blue we have it with public transport. So if we want to be sure that this is the information we are looking at, or if we want just to change this information, what we can do is just go on links over here, right click, graphical parameters, bars. Just for general information, you have several different types of graphical parameters, okay? You can have, for instance, different type of parameters based on the characteristics of the links. You can have different type of labels, for instance. You can have charts, plots as well. This is just one of the most intuitive, the bars that represent the information on the links. And as said before, here you have all the information that are currently plotted on the network for the links. For instance, scale attribute ID is the attribute that we are currently plotting. So in this case, for instance, we are plotting private transport volume in red. And if we click on this, we can choose, for instance, to select any different information. The type of vehicles that is plotted, the level of noise, add value is usually personalized. We can also, for instance, plot the current travel time on the infrastructure for vehicles, car. So, for instance, if I select this one, now I will see not anymore the volume, but I will see the travel time. And I can do the same for the public transport. So I can search for it and go on T-current for, where is it? Do we have it? There we go. And then we can clearly change the color. For instance, we want to go public transport in green because they are very sustainable. And we want to, yes, keep them in orange because we don't like them. And that's suddenly what you will observe. Now, as you see, I didn't pay too much attention here. So basically, the information looks a little bit awkward. You have always to be careful what you are selected and specifically double check if it makes sense to plot that information in the first place. You have a lot of information that will just return you a constant value if you plot it in the network in Visum because you simply didn't calculate it, for instance. So this is one thing. The second thing that I wanted to show, as I mentioned before, is the list of information for the links in the network. So in general, once again, you can do this for all the links in the network. You don't have to do it only for the links. You can do it for nodes, turns, traffic zones, connectors. You can go from list, network. You select the element you want, in this case, links. And as you can see, you will have the usual characteristics. And now you can always also use additional information, such as the volume of vehicles that use private transport according to the private transport assignment, and volume of persons using public transport. Once again, if you go here on the top where there is select attribute, you can also add additional information as we have seen in the previous slides. And this is it for the class of today. So for any question, once again, on either the traffic assignment or Visum specifically, you can always write me to my email from T1, and I wish you a nice rest of the day.